Hello, Larus.
Hello. Hey.
No. So Luca has written me that you are going to use a couple of devices or something like this.
No, in the end, I'm just using my computer and
Okay.
I'm just going to use PDF.
I see. Because normally I should. Okay, so now you're the co-host, so you can share screen.
Yes.
And if needed, you can annotate on your screen.
Okay. Well, that's fine. That shouldn't be necessary. I managed, I think, to.
I see.
I have very strange picture.
Hello, Larus. Hi. Hello, everyone.
Hi. Hi.
Hi, Irina. Hi, Alex.
Yes, there is something strange with my video.
Yeah, it's true. It's a
Yes.
bit,
Maybe I
You
will.
look a bit ghostly there.
Yes.
A little bit of impressionism there.
Yes, a little bit. I don't know how to security. Maybe I. Okay. Maybe I stop. It would be better.
Yeah, so we see your screen perfectly.
Okay. And you see just one page at a time, or?
No, now actually we see it like it is in a scrolling regime. I don't know how to.
Yes, I'm going to figure out. Here goes.
Yes,
perfect.
Yes.
That's good.
yes, it's exactly.
Okay.
Maybe we have 7-8 minutes still.
I don't know. Did you look asked already? Is it okay that we leave stream and keep recordings?
Yeah, Larus, can we leave stream or talk?
Sure.
Okay. I didn't ask for, sorry.
What it's worth.
Also, do you prefer like be interrupted during the talk for questions or at the end?
No, it's best to do it just as we go.
Okay, good. Very nice.
We still have 7 minutes, I
Yes.
guess.
Yeah, indeed. And for those who didn't switch time, we even have 1 more hour.
Yes. I see.
Hang on, I'm gonna.
Could you please make me my co-host?
Yes, you are.
Yes, okay. But something very strange with my video. Let me try one.
Sometimes it happens. Yes.
It's okay. Now
I
it's
think
okay.
the background you're using maybe is
Maybe if you switch off the background, then it may be normal. It will be normal. So.
No, definitely it will. Yes, there is no question about this.
Something wrong with the background. Yes.
By the way, Luca, I would ask you next time to remind me about time switch, because for the last seminar, I didn't notice that in US it already has happened.
yeah, but now it's fixed, no?
No, now it's fixed, yes, but for Nils' seminar, I just didn't realize that we are in Europe and in US, I mean in America, in US, Canada, they already have switched to another time.
I know, yeah. Indeed, I thought about that.
So for them, it was a little bit, well, incorrect in the, how to say, in the correct direction. So they could join 1 hour before. But in principle, just in case, all these small things, I mean, it's a bit too much for my brain. It's exploding with all of that. And yeah, send me your logo, please, with email, as I asked you.
Huh?
You send me a logo of Nordita in Telegram. I believe Telegram has wiped the idea of transparent background, because Telegram or WhatsApp, they usually change images a little bit on sending.
Okay.
Somehow they filter them. So if you have it just attached to email, it will simplify my life a little bit.
Okay.
I have written this to you in Telegram, maybe you didn't.
I didn't check it.
No, it's not urgent, but this happens.
I send it now. No.
Yeah, okay. I'll check it out. Yeah, now it is absolutely transparent. Yeah.
It's okay. No. Good.
Maybe we can wait a couple of minutes more. Just this number is increasing.
Okay, maybe we'll wait 1 minute more. Okay. Just people just coming.
By the way, Luca, there is one more request for next times. Can you remind me to turn on leave stream?
Okay.
Because normally I initiate it on Google and then I have to press some special button, something like start leave. Okay. And with Niels, it was also not so great because I missed his phrase or something like this.
Okay.
because I was thinking it's already done, but it was not. Now it's okay. Now it's already going. I just wanted to secure it, but just in case.
No.
Okay, maybe we can start now. Hello, everybody. Today we have a pleasure to listen to a talk by Larus Thorlacius. He will tell us about quantum chaos and unitary black hole evaporation. Please, Larus, 1 hour.
Thank you. Can you all hear me?
Yes, yes.
Very good. So yes, thank you very much for this opportunity to tell you about some ideas that I've been working with David Lowe at Brown University on that concern black hole information problem in the context of ADS-CFT. And they appeared in this recent paper on the archive. But we've, of course, been coming back to this problem over quite a number of years now, and maybe starting already in 1999, I believe it appeared, our first joint paper with David on the information, black hole information in ADS-CFT, in the very early days of ADS-CFT, and I think we've come quite a long way since then, and I want to tell you about our recent ideas here. So what I will be doing in this talk is revisiting the black hole information paradox in an ADS-CFT context, and we will be taking the n of the so the rank of the gauge group in ADS-CFT to be large, but it's important that it's finite so that we have a finite cutoff in our theory. And in this context, of course, if we take ADS-CFT as a definition of quantum gravity in this type of background, the question of unitarity resolves itself in the sense that we have a manifestly unitary evolution in the dual gauge theory. But then the issue is, how do we see semi-classical gravitational physics in the bulk arise, and also when do we expect it to fail? And of course, the black hole information paradox is first and foremost a failure of effective field theory. It's sort of an unexpected breakdown of the semi-classical approximation, and one would like to understand where does that, or put that into this context where we believe that we have a candidate for a quantum description of the problem. And so the steps will be as follows. So we want to think about the formation and slow evaporation of a black hole in a semi-classical context. Well, in ADS-CFT, that means we need to sort of identify states that correspond to, that are well described by a semi-classical theory. So we want to think about how do we construct in the gauge theory states that correspond to sort of weakly, diffuse infalling matter that forms a black hole. And then we also want to think about how do we describe the out states, the final state of the process with the outgoing Hawking radiation. So that's going to be the first step in the process, is we're going to use the Hamilton-Kabat-Lifshitz-Lowe construction to map from semi-classical initial states and final states to the dual theory. And then once we've identified actually states on a finite dimensional subspace, Hilbert subspace to work with that correspond to the formation and evaporation of an isolated black hole, some mass, we will consider the eigenstate thermalization on that Hilbert space And we will see that that actually allows us to, first of all, we'll see, at least in a formal way, how semi-classical bulk physics can arise. And furthermore, we can estimate the corrections to it. And we'll find that for typical black hole states, these are very small. There exist states where they can be large, and we can sort of characterize them to some extent. We'll also find that so we're getting a good semi-classical approximation for local observables outside, if we calculate expectation values outside a black hole. We can also follow the evolution sort of a specific set of infalling observers. There are some restrictions on that, but so we can, in fact, understand sort of how to holographically describe that at least in principle, in this formalism. And then at the same time, we will also see that this semi-classical description that we are seeing emerging from the eigenstate thermalization will break down basically a leading order if we're talking about transition amplitudes between early and late states. But that's maybe not surprising, because that's of course where the unitarity of the, one doesn't expect a semi-classical bulk theory to capture those. That is, of course, just the information problem. So this is going to be the outline of the talk. And well, if I get to the end, it'll also be the summary of, so let me first just take a step back and just think a little bit about how we formulate the information paradox. I'm not going to go into any details here, but simply remind you that the paradox arises in a context where we start with matter in a pure quantum state. And we're assuming that this matter can be described in a semi-classical theory of gravity. It's diffuse matter, no strong curvatures. And so this is then evolved forward in time, and matter undergoes gravitational collapse, forms a black hole, and then that black hole will gradually evaporate due to the Hawking effect. And in the semi-classical calculation that Hawking did, the outgoing radiation it's thermal. It does not carry any information about the in state. So basically this process will take a pure initial state and evolve it to a mixed thermal outstate. Will be this train of radiation. Of course, the radiation is the temperature of the black hole changes with time, so it's not just a pure thermal state, but it's certainly does not carry the information. So this, is an apparent violation of unitarity. But it's important to keep in mind that this is, of course, this whole setup that one formulates this problem in is a semi-classical effective field theory. And so let's, and it's also very important for the story that I want to tell today is that this whole process takes a finite amount of time. We form the black hole, it then evaporates. It certainly takes a long time if the black hole mass is large, but it's still finite. And this means that in a quantum theory, if we describe this as a quantum process, it's going to have a finite width. It's going to be very narrow, but it's going to have a width that basically goes as the inverse black hole lifetime. And I'll be working with assuming a 4-dimensional space-time. So that basically means it will be going like 1 over the mass of the black hole cubed. And this will be important in what follows. Okay, let me step back also a little bit and think about, since we're going to be doing this in the context of ADS-CFT, the black holes that we want to talk about are ADS black holes. And this is a slow process. So for, imagine we can form a black hole, it will then gradually evaporate, and we can assume that we have a quasi-static black hole that's going to be described at any given time to a good approximation by an ADS-Schwarzschild black hole. Assume spherical symmetry and no gauge charges in the game. And so I've written here the line element for the ADS-Schwarzschild black hole. I've written it in a form that kind of makes it manifest that if I put R equals to RH, which is the radial location of the horizon, then this will vanish. And we can then easily work out the Hawking temperature for this static solution. It has this form here, and it's plotted here. And these thing to note is that in asymptotically flat spacetime, which we can basically approach here by taking the characteristic ADS length scale, which is this capital L, take that to infinity, then we will see that this reduces to the expression that Hawking found in asymptotically flat spacetime. And but there's this extra term here, and this extra term is of course very important for ADS CFT. It turns this curve over here, and it means that black holes that are on this part of this curve here, very large mass black holes, they have positive specific heat. And, and these are referred to as large ADS black holes, basically when the characteristic scale of the horizon is much larger than the ADS length scale. And these are the black holes that are mostly studied in ADS CFT. They are relatively easy to study. They are stationary states. They are, in fact, they are basically, we can work with them using, on the field theory side, using fairly standard finite temperature field theory methods. And on the gravity side, we have this, they're static geometries. They are, of course, if you take the maximal extension, they're two-sided black holes. They are actually eternal black holes, and a lot of work has been the majority of work on black holes in ADS are involving these large ADS black holes. But what we are going to focus on today are the small ADS black holes, and this is because the small ADS black holes kind of are better suited to discuss the process of formation and evaporation of a black hole. The problem with the large ADS black holes is the fact that they are stationary states. They are, in fact, not evaporating. And if they do emit radiation, then that radiation will be reflected by the curvature of the ADS geometry. And one would then have to think about the problem. Basically, one has to then think about boundary conditions and things which kind of would sort of muddy the water when we want to think about the process of forming a black hole from an initial state and then watching it evaporate. And so already back in 1999, David Lowe and I pointed this out, that if you want to really think about the formation and evaporation of a black hole, you should rather think about the small black holes. And if you're on this branch here, the small black holes are basically just more or less ordinary Schwarzschild black holes in a cosmological background. And but the price you pay for that is that these are unstable states in the CFT. Well, it turns out we're going to turn that into a feature rather than a bug. The lifetime is of order m cubed for space-time dimensions, which means that these CFT states that we are interested in, they have a finite energy width. And that's going to be very important in what comes later. And we're in fact going to make the scales such that the entire lifetime of the black hole, so if you think about the distance that the Hawking radiation will travel from the first photons that are emitted, we want that to be small compared to L. So not only is the mass small, but actually this m cubed. And let me note, of course, that everything here is in Planck units. So so this is basically the lifetime of the black hole in Planck time units, given by m over, where m is measured in Planck units as well. All right. So these are the black holes we're going to be working with. And let's think about how do we get a holographic map to get a handle on these states. And the first thing is to think about the semi-classical initial states. We need to have enough of them to account for all the possible different black holes that we can form of a given mass. So basically, our set of initial states has to account for the Bekenstein-Hawking entropy of the black holes. And this was addressed in a very nice paper by Slava Mukhanov in 2003. And related ideas were also discussed by Zurek considerably earlier. And we'll come back to that, how we do that. But once we found those states, and those are going to be actually states that are so the overwhelming majority of them is going to look like, basically, if you want to think about initial states, they look like the time reverse of the outgoing states, which are basically, so they look like a train of incoming radiation that will form the black hole. You can form the black hole in different ways, but if you really want to account for the entropy, these are the states that you have to focus on. I'll talk about that a little bit later on. And then once we've identified those, these are basically then a collection of photons or gravitons that are propagating on our ADS spacetime. And before they form the black hole, they can be mapped using this HKLL construction to states in the CFT. And I will not go into the details of how one goes about that, but basically if you have a bulk excitation here, then HKLL showed that this can be expressed in terms of some smeared integral of primary operators in the CFT. So the picture here, this would be this is a figure from their paper. This is sort of depiction of ADS4 in global coordinates. The circle here is sort of stand-in for the S2. Then you have the radial R here, and then this all evolves in time. And so we're going to basically appeal to this construction, and we're going to make the assumption that this can be, in principle, worked out to arbitrary order in the 1/n expansion of the CFT. And as I said before, we're going to assume that we have separation of length scale. First of all, we want the black holes to be long-lived, so they have to have a mass that's large compared to the Planck mass. But at the same time, we want to arrange things so that their lifetime, the black hole lifetime, is short compared to what would be the light crossing time on the ADS. So that's basically so that we don't have to worry about how things get reflected back from the curvature, ADS curvature in our story. Okay. So this is going to be kind of the first step, is to identify the states that we want to talk about and map them into the dual CFT. And what we'll find is that there's the number of states that we need to work with is actually this. These states, they're sitting in a finite dimensional subspace or Hilbert subspace of the fold theory. Basically, the full CFT contains a lot of states that have nothing to do with black hole formation. We want to focus on those states that actually, if you set them up, you let them evolve, they will actually form a black hole, and then that black hole will evaporate. And that is a much smaller space, and it is basically has dimension which goes like e to the number. Yeah, it has that subspace is large, has a large dimension. It goes like e to the entropy, the Bekenstein-Hawking entropy, e to the m squared, but still it's finite. All right. Now, once let's think about what are these states that I want to construct. And the claim is that the majority of these initial and final states that are actually going to form this black hole. So the picture here is that time is sort of evolving here to the right. The initial state I want to consider about think about is a train of radiation. And this was the result of Mukhanov, is that if you really want to account for the full entropy, you have to think about all possible. So it's a train of radiation that comes in over a time of order, the lifetime of the black hole. So this basically, this D, I forgot to show it here on the figure, that's just the distance here. And this schematically is showing here that we have the hottest radiation is coming in first, and then it gets cooler and cooler. And of course, for most of the lifetime of the black hole, this would be, it is the red band here, the coolest part that is relevant. Now, if you just want to do the estimates, sort of to see that how things scale, you can follow the paper by Mukhanov. So maybe it's easier to count the outgoing states here on the right. So basically what you do is you think about an outgoing, you think about photons that are traveling outwards, and you only count those photons, let's say in this part of your space, that actually came from this small region here where the black hole was, okay? So that's a restriction on the solid angle, if you like, of the photons in any part of your geometry. And once you take that into account, and you simply count all possible states of photons that are moving, in a sort of a radial box of this size D, you find that when you most of them, you get that you maximize the number of states that you can get by this being thermal states. And what you find is free streaming radiation going outwards. And if you, now this is not done by Mukhanov, but presumably you would have to refine the calculation and think about the gradual change in temperature in the radiation as it's going out. But that's not going to change the leading order state count. And what you'll find is that these Mukhanov states, as we call them, they will, in fact, they are enough to account for the black hole entropy. In fact, you get an extra factor of sort of an order 1 factor that's slightly larger than 1, because this is free streaming radiation outwards. It's not an equilibrium state, so it actually, and that's fine, because that means we have enough states to on our Hilbert space. It's perfectly okay to have a few states there that then presumably when you think about the time reverse here will actually not form a black hole. But you do have enough states now to account for. And if we just stop for a moment and think about, for example, sort of the astrophysical processes by which we think we know how black holes form, like core collapse of a large star. Well, the entropy of a solar mass black hole is actually some 20 orders of magnitude larger than the thermal entropy of the sun. So those kind of states are actually fairly low entropy initial states that can, and kind of, that you can certainly form black holes, but they're not, you need these, they're just a small part of this Hilbert space that we're after. And in fact, by only counting these radiation states, we are picking up most of the states and only missing out on a tiny fraction. So I'm not going to worry too much about that.
So,
right. Yes.
Okay. So this argument is independent of ADS-FT, right?
Absolutely.
Okay.
And in fact, much of what I have to say is very independent of it. What we are going to use ADS-CFT is really more as a sort of, as a crutch, if you like. We're going to, through this HKLL construction, we're mapping onto a theory that we know has unitary evolution.
Mm-hmm. Okay.
And actually, of course, people are making a lot of progress these days with formulating holography in flat space-time. Ideally, one would want to do that for this problem. And then that would, I think these arguments in general for these timescales and these Mukhanov states will carry over.
Mm-hmm.
Quite.
So I'm not very familiar with Muganov computation, but is there any way in which one can change a bit the properties of this process to get the exact factor for the entropy?
I don't think it's been done. Slava, in his paper, tried to do that by letting the outgoing radiation have a slightly higher temperature. So he was basically thinking about this. He wasn't thinking about the full process here, but thought about sort of the quasi-static, sort of the balance of entropy balance for some time delta t during the evaporation, if you like. So sort of like a band in here. And then he tried having the temperature a little bit higher, and he found that in 4 dimensions, through a simple argument, he could actually optimize that to get a number that was pretty close to. But then when you try doing that in other dimensions, you find that actually it doesn't quite work. If you do exactly the same argument in higher dimensions, eventually you find that that factor is actually, you get less than 1. So, so I don't know that you can do that as a, to get the factor exactly right. But for our argument, it's not that important because we just need to have enough states to make our black holes. And this will give us that. And so, so for the remainder of the talk, the important takeaway is this, that we're going to be working on a subspace of the CFT Hilbert space that has quite a large dimension, but is finite. Okay, so now we're going to think about quantum chaos for a bit and see how that can be applied to this system. Now, quantum chaos is usually refers to sort of when you have a quantum system whose classical limit exhibits the usual dynamical chaos with exponential sensitivity to initial data and so on. But of course, any quantum system, particularly on a finite dimensional Hilbert space, can always be diagonalized in principle. And the energy eigenstates are going to exhibit standard, just phase evolution that is very certainly not chaotic. So there's a sense in which that quantum chaos is an oxymoron. But there's another sense in which it's actually a very useful concept, and that's also developed by, so these were ideas that were developed by Berry early on and then followed up on by Deutsch, and the formalism that we're using is due to Mark Srednicki, who I believe also coined this term, called it the Eigenstate thermalization hypothesis, which basically explains how you can have an initial state that's far from equilibrium, and yet will evolve in a system that satisfies this Eigenstate thermalization hypothesis, will evolve over some time into a state that is very hard to distinguish from a thermal state. An example of this would be if you have gas in a box and you confine it to let's say 1/2 of the box with some partition, and then you remove the partition. This is very far from being a thermal state in the for the full gas in a box, but it still seems intuitively very clear that it will evolve in a relatively short time to a state that will look very much thermal. And there, of course, this Eigenstate thermalization hypothesis is expected, and it has been sort of supporting evidence for it has been provided for certain systems, but it's not something that has been proved in general, and we're going to simply appeal to its validity rather than have we're not going to have much to say about that beyond that. But the mechanism at work in the Eigenstate thermalization hypothesis is that never, despite the energy eigenstates behaving very non-chaotically, the point is that if you take a generic observable that's not some conserved charge, it is actually not going to be diagonal with respect to the energy eigenstate basis. In fact, it will be far from that. And that is what allows chaotic behavior to emerge in a semi-classical limit. And again, I'm not going to go into any details, but rather just pick up some formulas from that formalism and see what they tell us. But yet still, it's important to keep a few things in mind. First of all, there should be a discrete spectrum of energy eigenstates, and they need to be densely spaced. That is, so that when we are calculating matrix elements of these observables that we want to work with, that we will get contributions from a large number of these energy eigenstates. And we'll find that this is extremely well satisfied in the black hole problem. And then what we should find then is that if we're thinking about localized wave packets in our bulk theory, that they will actually evolve in a chaotic manner. In particular, we want the dynamics sort of near the black hole horizon to exhibit that kind of behavior. And then when we have these conditions that go into the ETH, then we can expect a far from equilibrium initial state that should evolve relatively rapidly into what appears to be a thermal state. And this seems to be just what's going on in a black hole. If you think about the core collapse of a supernova, then, as I was saying earlier, the state that we start with is actually a low entropy state, but in a fairly rapid evolution, we will have ourselves a black hole that will settle down to a state that then will begin to emit Hawking radiation. Of course, for an astrophysical black hole, that's going to be an extremely slow process, but in principle, this is what we can expect to happen. And our expectation is that the thermalization timescale that you need to kind of wait before you can apply the ETH to your system should be of order the black hole scrambling time, which is sort of m log m for a four-dimensional black hole. All right, so how does this work for a black hole? Well, we expect it to work because the black hole exhibits sort of scrambling behavior. It's very suggestive of chaotic dynamics. This was argued early on by Sekino and Susskind in a well-known paper, Fast Scramblers. And the contribution basically in this new paper by David and myself is we want to now apply these ETH ideas on this black hole, the subspace of the Hilbert space that we've identified that is dominated by the radiation states, the Mukhanov states.
Sorry, Larus, there is a question in the chat by Robert Brandenberger. Robert, maybe you want to ask the question?
Yeah, so why do you expect the key time scale to be the scrambling time and not maybe the page time?
I think the black hole will start looking thermal long before the page time. You might even expect from classical physics, I mean, black holes settle down on actually timescales which are short compared to the scrambling time. They're usually just a few sort of light crossing times of the, so basically a timescale of order beta h is the timescale on which you expect the classical geometry to settle towards its slowly evaporating black hole. I think the scrambling time is relevant here because that tends to be okay. We'll see actually some evidence for that later on in the talk when if I at the very end, if I get there, that's kind of the time scale on which I expect if I'm thinking about an observer who's going to fall into the black hole, that is a time scale on which that observer will not actually be sensitive to anything that went into the black hole more than a scrambling time earlier. And so in particular, if you want to think about applying or developing a semi-classical description of infalling observers, then you would want to wait at least a scrambling time so that all the complications about the formation of the black hole will have settled down. So that's why I'm putting in this time. If it's the page time, then we're really saying that we cannot have a semi-classical description of a black hole until half the lifetime is gone. And I think that would be a defeat, if you like, in this context.
Okay,
all
thanks.
Right. So there are some, there are restrictions that I'm sort of not been going into here, but certainly what I mean by generic observable means, first of all, that it should not be a conserved quantity. It should also not be too complicated. It should not be an observable that involves so many operators that we're really talking about. It should not involve of order the m squared operators either. So it should be a finite set. And I want to think about observables that have a well-defined classical limit, if you like. They should not have any explicit H bar dependence in them. And the role of H bar is basically played by 1 over n for us. And then our main result, the result from Srednicki is, and this is based on ideas that were developed by Berry, is that we can expect matrix elements between energy eigenstates to have this following form: that there should be a diagonal part, which will involve a smooth function of the energy, and in our case here, and that's basically saying that. So I'll come back to exactly how smooth this function has to be, and then the off-diagonal parts are going to be given the off-diagonal contribution. So these are the sort of the failure of this to be diagonalized. They've been given by a random matrix. So this is the, so this can be, for example, in our case, we'll just assume a simple Gaussian random, that the entries are random Gaussian numbers. And then we will see where this will take us. Now, the prefactor here, we adapt to our problem. Basically, we have to, we can sort of heuristically understand how this prefactor comes about. If our observable is generic in the, it means that a squared should probably be then generic as well. And if you calculate the matrix elements of a squared, and then you insert the complete set of energy eigenstates, and you just use this formula and do a little bit of algebra that's done by Mark in this paper, you will find that in our case, remember the number of energy eigenstates that we're working with is of order e to the m squared. So e to the it's e to the Bekenstein-Hawking entropy. And then what we need to have here is a suppression factor, which goes like e to the, basically goes like square root of that. E to the is minus half of the Bekenstein-Hawking entropy. And the way you see that is that when you calculate the matrix element of a squared, to recover a formula that has the same form again, when you do this, you do a sum over intermediate states, and that sum involves an e to the s terms, but you're summing random numbers, and that tells you that that sum will actually only grow as square root of e to the s, and you need this explicit factor here and this is where the suppression of sort of violations of our semi-classical theory is going to come from. Okay, so this is going to be the basic formula that we work from, but it's important to note that while the observables that I want to calculate, whose matrix elements I want to calculate, right, are standard semi-classical, could be observables, bulk observables in standard semi-classical description of gravity. the eigenstates over which I am calculating there are very far from, they're very highly non-classical. So these energy eigenstates are some superpositions of ingoing and outgoing radiation states, and they have to be superposed for all different times in order to get a stationary state. And such states do not have a nice semi-classical description in terms of some simple space-time geometry. So this is very different from the case when we're thinking about large ADS black holes, which are really geometric states, and for which we can use finite temperature and Euclidean time methods to work with. However, the nice thing here is that even though the energy eigenstates are non-classical, we will find that when we do calculate this for these things for a in this basis of when we have the sort of a typical black hole formed from a typical Mukhanov state, then we're going to find that there is a we get nice semi-classical expressions, or what we expect semi-classical expressions to be. So there's some questions in the chat.
Oh yes, I just wanted to comment that ETH is very similar in its conclusions to a much older theorem by von Neumann called the quantum ergodic theorem.
Yes.
And that says roughly a similar kind of thing, which is that even within a pure state, you can find sort of thermal behavior. And
Yep.
so the way von Neumann does it is he says if you start with a generic pure state and you have under pretty mild assumptions about the Schrodinger operator, if you just evolve it forward, then you end up generically with something which is close to, very close to a thermal state, even though it's not actually a thermal state, it's still a pure state.
Yep.
And
and that's exactly what's needed here.
yeah, and I think furthermore, it even says, well, we showed that recently that it even says that generically you end up with a macroscopic superposition state as well. So I'm wondering if that will show up later in your analysis.
Well, I don't think it will, but maybe it should have. I don't know. In the sense we didn't ask that question. But okay.
Yeah, we can revisit. Thanks.
Yeah. So anyway, so these are the states that I'm working with, and I'm simply, like I said, these are energy eigenstates, and they must be there because I have a finite dimensional Hilbert space, and but they're not per se. So each you know, they're not perhaps not very nice states to work with, but okay. So now let's think about a typical black hole state. So that's going to be a superposition of these energy eigenstates that has a finite width. As we said before, the width should be of order m, 1 over m cubed. So I'm going to write basically such an expression. I'm going to basically write here that I have some linear combination on my, so the sum here runs over e to the m squared states. And it has basically this expression here, and I'm assuming that this delta E is of this order, okay? And then of course that tells us that the level spacing what we have is very, very small. It's e to the minus m squared. It's much smaller than this width. And so that then we're going to see, so this makes it very clear that we are going to be summing over an enormous number of energy eigenstates anytime that we want to calculate a matrix element. And we're going to see that there's going to be basically that this will affect a self-averaging. Now, the condition for this to hold in general was considered by Mark in his work, and we get a condition like this. So this function A that appeared in the over here, so it had to be a smooth function of E. Well, it has to be a smooth enough that its second derivative is much smaller than its own value by a factor of this width here. So this is just how the dimensions work. And this means for us, when the width is order 1 over m cubed, is actually not a strong condition at all. In fact, we would expect this to ETH to hold even for states where this delta is of order 1 in Planck units. But those states are, of course, those are short-lived compared to the black holes that we're interested in here. All right. So now let's think about how do we, so in a semi-classical description, we're not sensitive to the, to the microstate that we're working with. So let's imagine calculating this kind of expectation value for 2 different microstates and see where does the dependence on the microstate actually sit in the formalism. So I'm going to take 2 states, both be written as it can be expanded on the energy eigenstates. I'm going to, for convenience, I'm going to assume that they have the same expectation value in energy. That's just basically we want them to form a black hole of the same mass. But let's say for this argument here that their width is slightly different. So that there is a difference here in the width and sort of by order 1. So they're both have a width of order that's going like 1 over m cubed, but they can differ by some factor. And let's calculate the difference in expectation value. Take expectation value of some observable and in these 2 different and calculate the difference. And now we can use our formula from before. So we will basically put in this ansatz, if you like, for the eigenvalue thermalization, eigenstate thermalization, sorry. And if you just plug in these formulas, you'll find that this is given by an expression of this form. And then if you work on, so this first piece here is manifestly going to be diagonal. And then you're going to get the half diagonal pieces coming from this random behavior here. And then it's, one finds that the diagonal part actually only depends on these energy profiles. And so this difference only basically involves the difference in their widths. And then this is going to be, this we have assumed is a smooth function of the energy. So all the expression here is really only a function of the energy, the expectation value of the energy. And this is, of course, what happens, if you're doing a semi-classical description of doing semi-classical gravity, you would have a right-hand side on your Einstein equations that involves the stress tensor. And in a semi-classical, actually you get contributions from the expectation value of the energy. And so this is where we expect our semi-classical expressions to come from. And of course, it would be nice to work that out in detail for some model system, but this at least is consistent with what you expect for semi-classical gravity. Now, this, on the other hand, will manifestly, the off-diagonal piece will manifestly depend on what kind of a microstate you're working with. So let's look at that. If you take a typical small black hole state, that's basically, by that I mean you take pick at random one of these radiation states that we use to form the black hole. And then it's not hard to see that these off-diagonal contributions are in fact very highly suppressed. And this comes from the, basically comes due to this factor here. The contribution from the random matrix itself is of order 1, but you have this for a typical state. But this guy will suppress the contribution. So, and this of course is extremely small number for a microscopic black hole. And now you can of course get unlucky, and you might get a very large contribution. So that depends on the on what the microstate is. So there exist microstates for which this semi-classical theory would fail. And an example of that would be that if you take and you think about if your microstate happens to be an eigenstate of the random matrix, which is close to the largest eigenvalue that the matrix can have. Now, if we just assume that it's a Gaussian random matrix, we can use the semicircle law to estimate what is the largest. And it'll actually scale like the dimension of the Hilbert space, square root of the dimension of the Hilbert space here, which means that that will offset the suppression factor, and you can in fact get order 1 corrections to the semiclassical or the diagonal result. On the other hand, this is an extremely unlikely state to land on at random. If you write this maximum, the eigenstate that belongs to this maximal eigenvalue, let's call them C tilde here. And if you simply ask, if I want to get to close enough to this state that my C coefficients here are the difference is bounded by some small number, then you will find that the likelihood of actually landing on that state or such a state actually goes like this small number to an enormous number. So and of course, this is maybe not so surprising. Of course, it's also true that if you're sitting in a room, there do exist perfectly good quantum states where all the atoms collapse to some corner, and this is a very non-classical configuration, but it's also an extremely unlikely one. And so we're talking sort of that kind of probability here. Okay. Now, of course, you might think that if you could try to engineer such a state if you had very advanced technology, but that would take an enormously long time as well. You would basically have to engineer a state where you're projecting onto an energy eigenstate, and that we see that would actually require time of order 1 over exponentially long time scales, which kind of irrelevant to this problem that we're thinking about. All right. Now, this is not to say that everything that you might want to calculate is captured by these semi-classical approximation. If we have, so the picture here is that we form the black hole from some radiation, infalling radiation, and we have 2 ways to evolve that, to understand that quantum mechanical evolution. The first one is the usual one that we're used to, which is we think about this as a semi-classical state. We want to evolve it forward in a gravitational bulk theory. It'll form a black hole, and eventually, if we get too close to the singularity, or if we start thinking about unitarity, we will expect that to break down. So that's kind of a semi-classical evolution. But our construction sort of also allows us now to think about a manifestly unitary way forward, which is we do the mapping to the CFT state through the HKLL construction. And then we evolve that forward, and that will give us then, and then we could calculate S-matrix elements, if you like, or transition amplitudes, where we would then take, having evolved that forward, we would then calculate the overlap with some final state, which would be also then one of these Mukhanov states, an outgoing Mukhanov state. And then if we were to construct this using the unitary, using the CFT evolution, we would recover a unitary S-matrix. But we do not expect the semi-classical approximation to do this for us. In fact, even though both the in state that we start with and the out state, whose we want to calculate the transition amplitude to, are perfectly good semi-classical states that only involve low energy matter, we would expect the semi-classical evolution to give us a completely wrong answer. And that's not surprising, of course. That's just a rephrasing of the information paradox. But the way you would see that is you would calculate, or one way to see it is to calculate the semi-classical answer in 2 different ways. You can imagine evolving forward in time, the instate, and that evolution would, of course, take you through forming the black hole. Then you would get some outgoing train of radiation, and you could calculate its overlap with the outstate that you were interested in. You'll get an answer. But you could also imagine doing the opposite. You can imagine evolving backwards in time, the semi-classical final state. That will also give you an answer, but it'll be a completely different answer for this amplitude if you then try to calculate its overlap with the initial state that you had. So that's, yeah, so that is certainly a place where this will fail. Now, you would also expect it to fail for something like an entanglement entropy, because this is a non-local quantity. In fact, an entanglement entropy, in a sense, involves it's a fine-grained quantity that involves sort of a large number of operator insertions in some formal sense. And so you would expect that to give you the completely wrong answer. But of course, as we all know, there have been some remarkable progress on that in these years, which we have really very little to say about here. And I think also that whole development has very little to say about the problem that we're trying to address here. It's true that the semi-classical, we can augment our semi-classical theory with a prescription that tells us to calculate the generalized entanglement entropy. That'll give us an answer that will follow the page curve. Now, the page curve, of course, is going to be basically automatic in our case because our construction by mapping things onto the CFT, we will have unitary evolution, and therefore we're guaranteed to get page curve. You can also get that via a semi-classical computation. That is very interesting. I think it's not, some level it's not really understood why that is working. I mean, sure, we can formally discuss replica wormholes and the like, but it's still, I think, sort of that doesn't really get at the microphysics. But so there are certainly places where this we're not recovering semi-classical answers for everything here, but we are able to construct local observables that are far from sort of outside the black hole, and we seem to be getting the indication is that we will get that the semi-classical answers will be extremely close to what you would get from a, if you like, an exact calculation using the CFT. But a key thing then in you know for the information problem, you know, before we can declare that we've solved the information problem, we would have to ask, well, what happens for infalling observers? Are they going to, can we also have a semi-classical description of an infalling observer? And as far as we can tell, this is going to be true here as well. We can do the same kind of estimates for if we construct our infalling observables in the following way. So again, let's imagine that we start with some system from an instate which has a good semi-classical description. And then the procedure would be to build the observables that we want to measure for, let's say we want to think about basically a laboratory where people are carrying out tests of you know, space-time locality or something like that. And then you have the laboratory fall into the black hole. And you want to ask, can we make predictions using some effective field theory description of that infalling laboratory that can then be compared to what we would get in this unitary evolution that we're referring to here. And so the procedure would be the following. We start with something that will form a black hole. We're going to build our observables that we want to measure, basically in the following way. We build observables outside the horizon in some frame that is appropriate for infalling observers. Of course, there's going to be a Hamiltonian in our effective field theory that we also want to formulate then in this frame for an infall. And then we think about propagating this state across the horizon and ask what kind of answers do we get, because once we've done this construction, basically, so what I want to do now is in addition to the state that forms the black hole, I want to include in my Hilbert space also the degrees of freedom that are involved in the lab. And then I can do, before the lab falls into the black hole, I can map it using the HKLL procedure into the CFT. And it'll be a CFT, of course. The subspace will now be for a slightly bigger black hole that has absorbed the lab into it eventually. Then we can then evolve in the CFT and ask, and then use this ETH procedure that I described earlier to ask what kind of answers will we get for these observables that we have constructed to carry out whether it's some entanglement measurements for whatever we're doing in this infalling lab. And then the instruction would be to not send the lab in until at least the scrambling time after the black hole has formed. We can maybe get into that in a little bit later on if there's time. And then what one finds is that if, again, you're in a typical state among these Mukhanov radiation states, then you will find that you will have a large number of energy eigenstates that you're averaging over, and you will find that you would expect your semi-classical answers to be quite reliable for this. Now, of course, there are restrictions. The lab has to be small compared to the black hole. Well, that's true in any case. You want to think about a lab falling into a black hole and not a black hole inside a lab. And of course, ultimately in this description, a very interesting question to ask that we have only so far in some earlier work addressed in very trivial or oversimplified holographic models would be, how long do you expect the semi-classical approximation to hold? What is the time scale on which the semi-classical evolution kind of decoheres from the dual CFT evolution that we know can to sort of, on what time scale do you start seeing noticeable differences? Basically, your scientists in this lab would start seeing some non-local effects that they cannot explain using their effective field theory. Now, the indications were from these oversimplified models that was actually on a similar time scale, that the lab was, in fact, parametrically the same time scale that the lab would necessarily be getting close to the singularity. So that's kind of a nice consistency. But I would certainly be very interested in sort of addressing those questions in a more realistic holographic description. That's sort of something for future work. I think I've already used up my time, so let me but I can just maybe mention that there is a way to describe this effective field theory that I think is very sort of nice. That is that implements a cutoff on sort of in the radial direction. So this was developed by Corley and Jacobson in the late 1990s. Their motivation mostly was to try to come up with a formalism which allowed them to calculate the Hawking effect without sort of manifestly without having any trans-Planckian modes present in their theory. And they succeeded in this. So they had basically a lattice that was, they wrote a lattice theory in infalling Gauss-Strand-Panlevé coordinates, and found that they could explain, they could understand, they could see the sort of the source of the Hawking radiation in this context is from mode conversion in the lattice field theory, and And again, they used WKB approximation to actually do the calculation and found exactly the thermal spectrum that Hawking saw without any reference to Transplanckian modes, which on the other, in the standard treatment, and in many, in fact, most other treatments, they always sneak in somehow. You make some assumption about very high energy modes. Now, what we found when we applied the same model to actually follow, so they focused on what happens outside the event horizon. So we took the same model and thought about what happens when you follow it in. And then we found that precisely because you have a lattice cutoff in place, so you cannot, if you explicitly don't have Transplanckian modes, you actually find that this time evolution of infalling operators inside the black hole is completely insensitive to anything that happened more than a scrambling time earlier. And a corollary of that is that, of course, that it's also whatever these infalling operators, whatever effects they have, will all have been erased from the, for the, if you wait another scrambling time. And so this is one of the reasons why I suggested at the, that it's the scrambling time that is the operating scale for the thermalization of the system. Anyway, let me just flash my outline slide again. So we've been through the steps in the story. Clearly, there are many details that are that have not been worked out, and this is somewhat impressionistic, both certainly in my talk here, but also many, there are. I think this can be fleshed out on many levels, but I do believe that we actually have made some strides here in towards a sort of holographic description of the evolution of black holes in sort of that preserves unitarity on the one hand, and we can see where the semi-classical bulk description is coming from. And we can quantitatively see corrections to it and understand for what kind of states those corrections are small, and also have these rare events where these corrections would be large. Okay, but let me stop here. Thank you.
Okay, thank you, Larus, very much for your very interesting talk. Question, please. Raise your hands, please, to ask questions. I don't see. Ah, please, Shravan, yes. Please ask you.
Hello, thanks for the very nice talk. I have a couple of questions. First, maybe I didn't catch your point. So in the last conclusions part, at what time semi-classical physics break down? Is it page time or towards the end of evaporation?
Well, okay, sorry. There are, you have to, the answer depends on who's asking, in the sense that if you're a distant observer and you're following, you're looking at this black hole, then I would say that this construction actually, you have a unitary evolution if you appeal to the CFT side, and you don't, and also throughout that evolution, anytime after a scrambling time, you expect your semi-classical expressions to be very good approximations to what the unitary theory gives you. The exception to this is if you're asking questions that connect early time and late time states. Semi-classical physics is not going to capture those, and therefore, and that's not surprising. I mean, we don't expect it. And in a sense, what the unitary theory is doing is that it's actually resolving for you the strong curvature physics close to the singularity. Those states that describe the black hole at that point in time when there's very little left of it and it's very highly curved, well, there's a corresponding state in the gauge theory, which is perfectly good gauge theory state, but it's just non-geometric. It's not a nice state. But then that state will also then evolve, and it's our assumption and our expectation is that it will in fact evolve again to a nice semi-classical state, because that is what the black hole eventually will have. Well, okay, modulo maybe a few photons at the end that are very high energy, but so that's one answer. So that we actually have a semi-classical description for the entire lifetime of the black hole. The other answer, and a very interesting one, the question is, how long can somebody who's falling into the black hole expect his semi-classical bulk theory to be valid? And we know, of course, from the point of view of classical gravity, that we only expect that to be valid as long as, you know, curvatures are small. But there's another test now that we can do, which is at what point is the evolution, this forward evolution that we push into the black hole, at what point does that diverge from the exact evolution of this CFT state, that it would be unmistakable in the laboratory? And as I said, in some very, very simplified holographic models, which just involved some number of qubits that we could actually handle numerically, which meant not very large. We were seeing this time scale, we're seeing like a scrambling time, which is also the time scale that you, in this infalling Panlevet coordinates, that you can avoid the singularity for at most. Does that answer your question?
Yes. So just to confirm my understanding, so for a distant observer, like when we observe black holes, so semi-classical physics is fine, well, until the effects where higher curvature effects come from.
Yeah, until maybe at the very end. But that's only a tiny amount of the information will reside in the black hole by that time.
Okay. My second question is, well, in parallel with cosmology. So in cosmology, when we explain CMB, it is in the inflationary picture, it is all semi-classical physics. We don't need quantum gravity to explain CMB. So if my question is black hole special? Like, I mean, we special from the early universe, because semi-classical physics breaks down at some point. I mean, can I say like semi-classical physics breaks down only at the Planck scale, but not below it? Because in the CMB, you can explain everything with below the Planck scale physics, right? So which is like gut scale or anything.
Well, I mean, I don't have a parallel to this story for the cosmological setting, because I don't really know, I don't have a gauge dual. That and also, of course, there are maybe I should just leave it at that. I don't really know. I mean, it's clearly a very interesting thing to try to push these ideas in that direction.
Thank you.
Okay, let's go to the next question. The next question from Igor Valovich. Igor, please ask your question.
Thank you, Larus, for a nice talk. I have the question concerning the ETH formula. Could you please show it again?
Yes, hang on. There it was, right? Yep.
Yes. You said R is a random matrix.
Yep.
But it cannot be so, because the left-hand side is deterministic. So the deterministic matrix element cannot be random.
Yeah, no, that's true. But I think the idea is that you have some complicated dynamics going on, which you in a sense you're modeling with this random matrix here.
Yes, but I simply say that in this form, this formula cannot be true.
No, but it could be useful.
Okay, I have another question. frankly, I don't understand. Do you suggest that semi-classical gravity is consistent with ETH or not?
What I'm trying to argue is that ETH will allow us to sort of identify states where we expect, states for which we expect semi-classical gravity. At least some questions can be about those states can be answered by semi-classical gravity. Yes.
So the answer is yes, consistent.
Well, I also pointed out some things where ETH is not going to help you. You know, there's semi-classical gravity simply cannot answer questions about, for example, these transition amplitudes.
Okay, thanks.
Okay, I see one more question. A question is from Andrei Pardashov. Andrei, please ask your question.
Hello.
Hello.
Hi. Can you hear me?
Yes.
Yes. So my question is about the CFT interpretation of the story. So if we consider dual CFT, then large N, or equivalently thermodynamic limit, plus the ETH, more or less equivalent to the statement that an expectation value of, let's say, a stress tensor. Well, let's also consider a particular operator, for simplicity, a stress tensor. Let's consider expectation value of the stress tensor in a heavy state. Then the expectation value of the stress tensor thermalizes. And that's equivalent to ETH plus large N. But when we say it thermalizes, the corresponding thermal state is, is the usual state which wins in thermodynamic equilibrium, which means it's either the large black hole or it's the thermal ADS, depending on what your mass is. So I was just wondering, what is the role of this story in that description, and like, is it that you're considering some special? It looks like you're considering some special states, some special subset of Hilbert states which are relevant for small black holes.
Yes.
Or is it some? That's the issue.
That's the issue. Yes, it's and those are very unstable states. They're not. They're certainly not thermal equilibrium states.
So these two stories, it's not easy to connect them.
No, I think your story that you referred to connects very easily, or more easily, to the large ADS.
Yeah. But to a small one.
Yep.
Okay, thanks.
Okay. More questions, please?
There are questions in the chat, actually, by Robert Bannenberger. And,
please, Robert, ask your question. Or it's just a comments? No, okay.
No, it was a question. Larus, what does your analysis imply for the singularity in the classical black hole solution?
It just implies that at that point, the semi-classical description manifestly breaks down. I mean, and we would all agree about that, because it is always, assumes that we do not have strong curvatures. From the point of view of the unitary evolution, it's still the state that you evolve from the early Mukhanov type state is a perfectly good CFT state that you can evolve forward. I don't really have a good handle on exactly what it looks like, but it's sort of I'm using the CFT more sort of as I have that state in principle there. Now, of course, if I could calculate that, that would basically have resolved for me the black hole singularity. So that's kind of implicit in this story that it gets resolved in this sense.
Okay, thanks.
Okay. More questions?
There is Dima in the chat.
If there are some questions, some notes in the chat, just tell everybody. Dima, Agiv, do you want to make some comments or ask?
Yeah, I would like to question Larus. It's known that ETH implies some restrictions on just if you consider some correlators, for example, some density metrics.
Mm-hmm.
It would imply, for example, just ordinary ETH applied to quite an arbitrary two-point function. It will imply bound on fall-off in momentum space. And if you consider OTOC or four-point function, ETH straightforwardly implies MSS bound on the Panoff exponent and growth of four-point functions, in other words. And what the restriction would be for your setup, you consider some amplitudes or something like this, probably it will set up some bounds, or this is not applicable here.
Well, I think, well, it's
like you consider also
I think the
some
tricky part would be to decide which operators you want to actually calculate your these correlation functions for. Now, of course, the HKLL construction gives you operators that are quite non-local in the CFT side. And so it may be that these, that it's as simple as that the things which involve, it might just be hard to apply these restrictions because the operators that you're actually doing the calculation with are actually much less local than you might think. But it's certainly something that's very interesting to look into.
Okay.
Okay. I don't see more questions. If somebody would like to ask question, please do it just now.
Maybe I can ask one, which is
okay,
yeah.
please.
So it's partially related to the talk. It's more about quantum chaos in black holes. Okay. Like usually people say that black hole seems to be the most chaotic systems because maybe they can scramble information in a m log m time. It should be basically maybe the shortest possible time. And so
yeah, I'm kind of in the last part there. I was sort of appealing to that. I think these are, ETH might be applicable even if they weren't quite so fast anyway.
Okay. So let's say the question would be like, given like, how could we, even some astrophysical black hole, okay? What's your opinion about like how can we test these quantum chaotic properties of black holes? Like if you would try really with astrophysical black holes, is there a way to really test these assumptions sometimes people make about black holes, like that they are very chaotic and I don't know what?
Well, I don't have any obvious any good answer to that, I think.
Because if you think just about thermalization, like you perturb a black hole, you see some quasi-normal mode. The quasi-normal mode is, I mean, like the time scale of this quasi-normal mode is anyway proportional to like GM. So sometimes
right. So that's actually shorter than this.
So maybe that's not what.
And I suspect that it's kind of hard to, for astrophysical black holes, m log m is already somewhat long, not enormously long, but it may not actually be long enough to to parametrically separate it from a few GMs. So I think for astrophysical black, I mean, we're working here with, in this whole story, of course, we're sort of assuming parametric
Sure.
scaling and separation. And
yeah, because it would be nice to see some effect even like
of course,
outside black holes, like of this quantum chaoticity.
yeah.
Okay, thank you.
Okay. More questions, please? If not, let's thank Larus again
Thank you very
for
much.
his very interesting talk. Many, for me, many unusual ideas. So we will wait for your future talk. Okay, thank you.
Thank you, Larus.
Thank you.
Thank you.
Thank you very much. It would be nice if you can send your file so that we will upload it to the website.
Okay.
Sure.
Very good.
Do that.
Thank you.
Bye.
Okay, thanks again, Larus.
Yep.
See you, everyone. Bye-bye.
Bye-bye.